and please, Giacomo, come on the stage. It's working, yeah. Okay, so as the last talk before lunch, we have Giacomo again, who's going to tell us about vinaigrette, an MPC approach to distribute unbalanced vinegar and mayo signing. Please go ahead.
Hello, I guess the title is right for the lunch. Anyway, hello again, I am still Giacomo. This is another project, it's a talk about another submission, still to the threshold call from NIST. This time, based on, again, on a different assumption. Before we saw isogenies, we saw lattices from Sophia, we saw ash base from the previous talk, and now we are speaking about oil and vinegar based schemes. The reason for this submission is, as for the other ones, that there is a general interest in threshold schemes, and in particular post-quantum ones. And a particular reason for this submission is that oil and vinegar based schemes seems to be particularly prone to be distributed using generic MPC techniques. And the second reason is also that there is a, let's say, more particular interest in schemes that are potentially to be standardized. And it's fair to say that two OV-based schemes, UOV, unbalanced oil and vinegar, and mayo, are potentially on track for standardization. This is still an open process, but there is some non-negligible probability for this to happen in the future. So, for this talk, the idea is to first give an overview of the oil and vinegar framework. The goal is not to explain the framework, just to give an idea on why this is prone to be used with MPC techniques. So I won't go into details about the mathematics. And then we'll see how to distribute it, what are the main building blocks, and what are the limitations of this approach. Then we'll give some preliminary results from our implementation and discuss some potential ongoing work that could benefit from additional research. Okay, so the main idea of the oil and vinegar framework is that you have a quadratic map from a domain to a codomain, and what you want to do during signing is to find a pre-image, a random pre-image for this quadratic map. If you want to do some nice picture, essentially we are searching points on an algebraic variety. Okay, this is mathematics, but it helps the intuition. And sadly, we are constrained by being three-dimensional creatures. Otherwise, I could have done much nicer picture, but we'll have to stick with this two-dimensional quadric. And the idea, okay, sorry for the mathematics. The idea is in oil and vinegar-based schemes is that the trapdoor is a linear subspace of this zero locus of this map. So it's like, in this case, it's just a line. And when you have this kind of trapdoor and you want to produce a signature, you are essentially searching for points over this linear space. And a little note, this is the intuition of UOV. In Mayo, the situation is slightly different, but just because you essentially bootstrapping a smaller quadratic map to get a more secure, sorry, not more secure, but bigger and easier to use quadratic map. However, the intuition, like the core intuition of what is happening is still the same. It's just that like you build this quadratic map in a slightly more structured way. However, coming back to designing, the idea of designing, as I was saying, is that you take this complex to work quadratic map and you collapse it to a linear space. And then signing is essentially equivalent to solve a linear system that is a relatively simple operation. Here I summarize all the procedures that need to perform during signing, and as you can see, okay, there is some hashing, but this hashing is a public hashing because oil and vinegar based schemes are what's called a hashed and signed scheme. So you don't really need to perform this hashing on some kind of secret data. Then there is the second phase that essentially requires the preparation of this linear system, the collapsing of this algebraic variety. And this can just be performed first with some multiplication and then with some linear operation that are listed here. These OV-based compute A and compute Y are just some linear arranging of the inputs. Sorry. Then you need to perform some shifting, some message-dependent shifting. Then you need to solve a linear system, and this is the core operation of the scheme. And then some other multiplication and linear operation to transform this solution to a signature. And so the most important operation to perform for distributing this scheme is essentially solving the linear system. And this is not an easy task in general, because it's an easy task when you want to do it on an handbook, but in practice, if you want to do it for a threshold signature, you need to solve this linear system in an oblivious way. That means that both the system and the target, so the matrix A and the vector B, are shared between the users, so you don't there is no single parties knowing them. And what you want to get is a solution to this linear system in such a way that the output is still distributed between the parties. This is a known problem, and the first solution came up a few years ago from this paper of Kotz and Smart about thresholdizing post-quantum signatures. And what they proposed was to do what's called one-side masking. So you have this shared linear system, and you randomize it on one side. This is an efficient procedure. However, it will leak a lot of information about the linear system in the case in which this system is not full rank. In particular, we left the kernel that, this may be a little technical, but intuitively it's a lot of information about the secret key, since this linear system depends on the public key. So Sophia and Daniel and Guillem last year came out with a different solution that consists in randomizing the system both on the left and on the right side of the system. This complicated the MPC operation. However, it makes the procedure more secure, because in the case in which this system is not full rank, then you will leak only the rank of the system and not any information about the kernel, for the dimension of the kernel. However, this procedure is more costly. It requires 6 rounds of online operation and 3 matrix-to-matrix multiplication. But it's possible by rearranging the operation, and we are doing that in the submission, to perform this operation in a more efficient way. However, this would still leak some information about the rank. Recently, I just wanted to mention that a new paper came out trying to solve also this problem by computing the rank of this matrix in MPC also, so performing essentially a determinant computation with generic MPC techniques. They show this to be feasible. However, the overall cost is non-trivial, and so it's really a question about is this worth or not, to reduce the leakage to this point, that is the minimum possible, but paying this high price during the computation. And this was about distributing the system. That is clearly the most important part on which we need the most important computation that need to be performed during the threshold signing. However, and this leads immediately to a distributed signing procedure for Mayo and UOV. However, the question that we would like to answer is it possible to do better, if you want to actually deploy this system? And to do that, we need to look closely at the scheme. In fact, here we have to compute the first step consists in computing the target vector that depends on the message that is public and the salt. and the salt can actually be pre-computed. And second, another thing that we can observe is that here there is, like, if you look at the multiplication depth of the protocol, here at the start in line 8 and at the end in line 16, there are some multiplication by secret values, but it's possible to rewrite the protocol in such a way that we avoid this multiplication and so reducing the multiplication depth of the protocol. These are some costs because it makes everything more complicated with respect to the system solving. However, like in an MPC scenario in which we are trying to reduce the number of online interaction could be worth. Otherwise, another idea could be to pre-compute the multiplication that need to be performed at the end for preparing the signature. Also, other remark we can do is that the linear system A and the vector Y are independent on the message, so they can also be pre-computed by the parties. And also their multiplication can be pre-computed, and in particular the multiplication by the inverse matrix. And also this inverse matrix, a to the minus 1, doesn't depend on the message, so can be pre-computed. The only thing actually here in all of these protocols that actually depend on the message is the vector t. And this is like the only operation that actually need to be performed during online signing, plus the multiplication of this vector by the matrix a to the minus 1. But since this vector t is a public vector, we're essentially multiplying like a shared matrix by a public vector, and this can be performed locally. And so, putting this all together, we saw that it's possible to have like a pre-processing phase that allow for only one round online phase. More precisely, the pre-processing phase would essentially consist in first generating the vector v, then performing some local or online operation depending on the choices that we made in the protocol. We can choose if to optimize, let's say, for the arithmetic efficiency or to optimize for the round complexity efficiency. Then we need to construct the system, and this is again a linear operation, and to compute the target vector, again a linear or quadratic operation depending on the choice of the protocol. And then we need to solve the system, eventually restarting, but this again happened during the preprocessing phase. And then, okay, supposing that we have finished all the preprocessing successfully, whenever we get the message, we need to first compute the target vector. If we pre-computed also the salt, this is a local operation, otherwise parties need to interact online to sample a random salt. And then they just need to compute some local multiplication and obtain something that is actually a shared signature, and they only need to open it online to get like a signature. And so essentially what we got is a partially non-interactive protocol that is still fully interoperable with single party OV-based schemes like Mayo and UOV. Here I've summarized the round complexity. The first line is the first work by Daniel and Sofia, in which we are focusing on the feasibility of the construction and on the security. And here, like for the submission, we're actually not only focusing on these important topics, but also in trying to improve the online efficiency and round complexity of the protocol. So depending on the trade-offs we want to aim for, we have essentially between 7 and 5 rounds of execution, and the one that actually depend on the message are 2 or 1 depending on the design choices. Okay, so let me close with some preliminary performance from our implementation. It's an implementation in Golang with active security given by the use of authenticated message codes in a SPDZ kind of way, in which we check every operation via Mac. And here in this table, we have inserted like different timings. These are the online timings. In the bracket there are the total timings, so pre-processing plus online operation. And these are given for Mayo, but they are similar for UOV and different kind of parameter sets. And there are there are different threshold profiles, but we also give different possible way to instantiate the scheme. The first column is essentially the same protocol as the first one proposed by Sofia and Daniel and Guillem, with some little net improvements that we discover while doing the submission. And then in the second and in the third column, there are the actual schemes that we plan to submit. The first one that aims for arithmetic efficiency, and the second one that aims for round efficiency. So trying to reduce as much as possible the number of rounds. And as you can see, we actually get some very efficient scheme with respect to the online signing time. And even if the pre-processing is actually costly, it's still, first of all, they are all in the same range, in the same ballpark, and potentially deployable in practice, and with some, let's say, space for improvements. And these timings have been performed without any multi-threading, but in practice we can expect that a part of the computation should be performed in parallel by the parties. And this, thanks to this implementation, we can also compare it to other scheme, in particular to lattice-based threshold post-quantum scheme. And as you can see here, actually, we are the fastest scheme with respect to the online complexity, online signing time. Okay, let me close with some potential new direction and ongoing work. First is a security analysis. This is usually like a cryptology-related question, but is also an MPC question, because as I was saying, the most important problem to solve in general for oil and vinegar-based schemes is to understand their security and the security of the leakage. And there are some MPC solutions that can try to solve this problem from in practice using MPC. Also, another, let's say, open question for security is how to get active security, in the sense that we already got it using some message authenticated codes in a sort of naive way by authenticating any operation. But it's a nice question, interesting question to ask, okay, what are the actual operations that we need to authenticate, and at which point do we actually need to authenticate them? Maybe we can, let's say, avoid some MAC checks or postpone them until the very end of the protocol. Other questions are possible improvements to the protocol. Okay, we already tried to improve it a bit, but for sure there are better ways to do so. For example, finding best way to perform the matrix-to-matrix multiplication that are the actual bottleneck to the efficiency of the protocol, or maybe generate the correlated randomness in an ad hoc way, since we already know the way vinegar vectors are going to be used, this random vector B that are sampled at the start. Maybe there is a way to sample the randomness that is, let's say, then better to be used during the protocol execution. And also some ongoing work is on the action implementation. As of now, we have a Golang implementation that is not constant time, was not supposed to be, but we need to do so. And there are some part of the protocol that are now written in assembly optimized arithmetic, but we'd like to extend the amount of optimized part of the protocol. Another work in progress are with respect to the actual emulation of the network, to actually see the impact of latency in all our protocols, in particular both during the preprocessing but also in the online signing phase. And then the integration of some more complex correlated randomness generation. We can do it, let's say, in a naive way, just by generating pivot triples, but the efficiency improvement we would get by generating actually matrix pivot triple probably are non-trivial, so we are considering them. Thanks for your attention, and happy to answer questions.
Okay, so we have time for questions. Who's interested in asking a question? All right, so I may want to ask actually two. So one is, can you go back to the previous slide, please? Yes, here. So what do you mean by not constant time? Because nobody knows the secret. Like no party is running code that depends on any secret. So I guess you mean the leakage, right? Because when you leak this, you have to try again, and this leaks information of whether the. But in a normal, let's say the MLDSA, it has no leakage. The runtime may or may not be constant, but it should not depend on private data because nobody knows the data, right?
Okay. Well, yes and no, in the sense that suppose that we are in an out of n scenario. If n-1 users are corrupted, the last user will actually hold all the secret. So he's actually performing, let's say, when he computes some multiplication by O and some other value, this actually depends fully on the secret. So if this secret data, let's say, is influenced by having a lot of zeros, like the runtime is influenced by having a lot of zeros, this would leak some information that
100% makes total sense. And the last, do you have more questions? Okay, just to close, it's funny you were the first talk and also the last talk, and you touched on isogenies. Then we saw hash based, then we saw well in different order also lattices. So will you dare to say that the most suitable post-quantum scheme for the threshold setting is OV type? Would you feel comfortable claiming that?
not in general, because let's say no, a general problem for OV-type schemes. Okay, let's assume that we are fully sure that they are all secure, because there are also some security discussion. I guess that the scalability to higher security level is not obvious. Let's say they don't scale so well in general, OV-type schemes. So even though I fully agree that if we look at NIST level 1 security, OV-type scheme are likely to be the most efficient one for threshold deployment. For higher security level, I didn't look at the number, but I would bet, like as a rule of thumb, that the additional cost that you have in general, like the cubic scale that you have for OV-type schemes, would kick in even in threshold scenario in which I guess the arithmetic become even more expensive.
This makes sense. Okay, so no more questions? We have one.
Do you have any performance measures about the OB applied to K-check accelerators? KECC, K-check, yes, yeah. No? Okay,
Okay, so in that case, let's thank Giacomo again. We are free to fill our bellies. Let's go.